Hi, I am Sagar. In this video, we will discuss solution for few previous year gate questions on combinational circuits. This question asked in GATE ECE 2017 set to 2-mark question, the two numerical answer type. Figure 1 shows a 4-bit ripple carry adder realized using full adders, and this figure 2 shows the circuit of a full adder. The propagation delay of the XOR and propagation delay of AND gate and propagation delay of OR gate is 20 nanosecond, 15 nanosecond and 10 nanosecond respectively. Assume all the inputs to the 4-bit adder initially reset to 0. Initially all inputs are 0. At t is equal to 0, the inputs to the 4-bit adder are changed. The x is 1100 and y is 0100 and z not equal to 1. The output of the ripple carry adder will be stable at t. 4-bit ripple carry adder. So 4-bit ripple carry adder. This is the full adder circuit. If you see the circuit diagram of 4-bit ripple carry adder in terms of full adder, x0, y0, x1, y1, x2, y2, x3, y3, and this is the z0, this is the sum s0, s1, s2 and sum s3. So now this is the z1. Now here this is the z1, z2, z3 and this is the output carry z4. Now initially this 4-bit adder reset to 0, means that S0 is initially S0 is 0, S1 is 0, S2 is 0 and S3 also 0. Then carry from one full adder to another full also 0. At t is equal to 0, the x become 1 1 0 0. So 1 1 0 0. The y become 0 1 0 0 and z not equal to 1. After applying this input 1 1 1 0 0 1 0 0 and z naught is 1, then after applying this inputs, now s naught become 1, okay, after 40 nanosecond. So we have two XOR gates. After 40 nanosecond, then s naught become 1, and after 10 plus 15, 25 nanosecond, this z1 becomes 0, this z1 becomes 0, and even here after 25 nanosecond, to get this z1 we require 25 nanosecond. So now here also s1 is 0 and z2 also 0 for this 0 0 combination. Now if we observed, yet this 25 plus this 20, at 45 nanosecond this s1 is 0. Similarly this 25 plus 15, 40 plus 50. So yet 50 nanosecond, then z2 is 0. If you observe, so the z2 value is 0, this z2 value is 0, yet t is equal to 0 as well as at t is equal to 50 nanosecond also. So now this s0 will get after 40 nanosecond, s1 at 45 nanosecond. So at t is equal to 0 also, that s1 is 0. There is no change in s1 and z2 even after 50 nanosecond, or at t is equal to 0 also same value. So we don't want consider delay for these two full adder. If we calculate the delay for these two full adder, these two MSB bit, then that is the minimum total delay of this addition. So this Z2 is 0 when t is equal to 0 and t equal to 50 nanosecond. So now we have to calculate the delay for these two full adders. Then only we will get the minimum delay, the total minimum delay for this addition to get a stable output. In this circuit, at A, the waveform at A becomes stable at t equal to 0 itself, because that applied input combination does not cause any changes at this point A. The Z2 is 0 at t equal to 0 as well as t equal to 50 nanosecond. Means that waveform at this point A becomes stable at t is equal to 0 itself. And at this point also, the output is stable at t equal 0 itself. Even before that input is 0 0, that XOR gate output is 0. Now input is 1 1 1, the output is 0. So at this point also, the waveform at this point also stable at t equal 0 itself. So this S2 will get at t is equal to 20 nanosecond only. At t is equal to 0, this point and this point both are stable only. So S2 is equal to 0 when t equal to nanosecond. This Z3 is available at, here t is equal to 0, this is 0 nanosecond, so 15 plus 10, here 15 plus nanosecond. So here at Z3 is available at 25 nanosecond. So this is the 0 delay already, here 15 is there, 10, 15 plus 10, at 25 nanosecond Z3 is available. So now this Z3 is the input to this circuit. And one more point if you observe, so at this location, now if when the before input is 0 0, that AND gate output is 0, now input is 0 1, then this also 0. Now at t is equal to 0 itself, this point here also the waveform is same. So the waveform at this output of this AND gate is stable itself, because the applied input combination does not cause any changes at this point, similarly at this point and at this point. So here to get this Z3 we require 25 nanosecond. So now this XR required 20 nanosecond. So to get this S3, so we required 45 nanosecond. 45 nanosecond. So Z3 equal to 1 only when at t is equal 25 nanosecond. At t equal 45 nanosecond, S3 is 0. At t equal to 0 nanosecond also S3 is 0. Similarly, at t equal 20 nanosecond, S2 is 0. At t equal to 0 nanosecond also S2 is 0. But to get this S0, we required 40 nanosecond. 40 nanosecond. Now if you observe, to get this Z4, so here the input is NAND gate required 25 nanosecond, here 25 nanosecond. So this is the 15 plus 10. So 50 nanosecond. After 50 nanosecond, the Z4 become 1. Now if you observe, S3 is 0, S2 is 0, S1 is 0. Even at t is equal 50 nanosecond, 45 nanosecond, 20 nanosecond. Even t is equal 0 itself, okay, S3, S2, S1 is 0. Now S0 is equal to 1 only after 40 nanosecond. Now this Z4 equal to 1 only after 50 nanosecond. The output is stable only after 50 nanosecond for the given input combination. If for other input combination required more time, because that carry is propagated from one full adder to another full adder. So it required more time. But for the given combination, the Z2 is 0 at t is equal to 0, at t is equal to 50 nanosecond. If you see these 2 points, here at these 2 points, okay, at these 2 points, especially at these 3 points, okay, the output at these 3 points, the value is same even after 50 nanosecond and at t is equal 0 also, because that applied input combination does not cause any changes at this location. That's why we'll consider from here only. So now after 50 nanosecond, the Z4 become 1. So that minimum time required to get stable output is 50 nanosecond. Answer is 50 nanosecond.